Let's see. So I guess the first thing I should say is that I was honored when I looked at the program a few weeks ago and discovered that I had been scheduled to give a talk on Bell. So thank you to the organizers. The title that appeared in the conference program was something about appraising Bell and his contributions to the foundations of quantum theory. I guess it's clear from the poster that the organizers have a very positive opinion of Bell and his contributions to quantum theory, and certainly people who know me and that I've talked with this week know that I share that positive opinion. But there's something a little weird about giving a talk for an hour about how right Bell was or something like that. So I decided to take the liberty that others have taken and switch the title slightly. Instead of really appraising Bell, I'm going to try to help us all appreciate Bell a little bit more. My philosophy or, sort of motivation or approach to trying to do this is more or less based on the fact that I've never known anyone who I thought actually understood Bell well that had a low opinion of his work. So my hope is that if you get to know Bell a little bit better, then you will come to share my positive appraisal of him. This is a picture of Bell contemplating a snow globe that I believe was either made for him or given to him by Bertelmann's wife. And I put this picture here because I sort of feel like this is not a very serious talk in a certain way. This is the kind of talk that maybe we should have had last night, sort of like sitting in leather chairs, smoking cigars, and drinking beers together at the end of the conference. And this is, the closest picture of Bell that I could find that captures something like that spirit. The talk will occasionally include random quotes from other people about Bell that I found when I was sort of doing some biographical research about him. So here's one just to get us started. This is something Roger Penrose wrote after Bell's death. In my opinion, John Bell performed an extremely important role in generally supporting and thereby making respectable the apparently fringe activities of such people as Bohm, Pearl, Ghirardi, and many others, including myself. That is Penrose, not me. In suggesting schemes that go beyond standard quantum mechanics in the intended direction of realism. No physicist could doubt the scientific credentials of John Bell. The fact that he was prepared to go out of his way to support research of this kind gave it a previously unaccustomed status. And I think this captures sort of maybe the fundamental point that I think we should all have in mind, that without Bell, literally none of us would be here, not just in the sense that this conference certainly wouldn't be happening, with a picture of John Bell on the poster, but literally I think this field of sort of the foundations of quantum mechanics simply would not exist. So we all really owe a great debt to him. So here's a kind of outline of what I'm intending to do. I found in discussion with someone who will remain nameless a couple days ago that some people know very little about sort of what Bell did other than the foundations of quantum mechanics, and he actually did a lot. And so I wanted to give a kind of biographical sketch of him that will help you appreciate the breadth of his contributions. And then basically the bulk of the talk will be somewhat random and disorganized sequence of things that Bell said on various topics that have been sort of recurring themes in the meeting. And so it's a kind of opportunity to reflect on what Bell might have said about some of the issues that we've all been worrying about this week. Good. So jumping into sort of quick biographical sketch. Bell was born in Belfast in Ireland in 1928, and I was happy to learn a few weeks ago that the region of Belfast apparently that he was born in is called Tate's Avenue. My younger son is named Tate, and so now I'm pleased to be able to claim that he was named in some indirect way after Bell, even though I didn't know that at the time, but it's still cool. His parents were named John and Annie, and he had an older sister and two younger brothers. Someone, Andrew Whitaker, who's done some biographical work on Bell, wrote, "From an early age, John used encyclopedias and other books of reference to generate large collections of facts on which he would lecture to any of his family prepared to listen. Indeed, he became known in the family as the Prof." This is like at the age of 11 or something, I believe, the remark. So he went to high school, and then he went to university in Belfast. He actually sort of took a year off between high school and going to college, where he got a job sort of working as a technician in the teaching laboratory in the physics department at the university. You know, like he describes it somewhere as sort of his job was to like lay out the wires for the physics students so they could do their, you know, electricity laboratories and stuff. And while he was there, some of the faculty members sort of recognized his brilliance and supported his entrance into the physics program as a student, and I think helped him get a scholarship. And there's another sort of amusing anecdote. Bell was an outstanding student though his lecturers at times, so this once he became a student, may have found him something of a handful. He himself has told how he clashed with one of his professors, Dr. Robert Sloan. This is one of the people who had sort of recognized Bell's talent when he was working in the teaching lab and sort of helped him become a student there. But he ended up arguing later with this professor on the meaning of Heisenberg's famous uncertainty principle. But who or what, Bell persisted in asking, decides what either delta x or delta p actually is? It seems that Sloan had no answer, or even worse, he tried various forms of words adapted from the rather bland formulations of Niels Bohr, which Bell denounced as meaningless. Poor Dr. Sloan, a man of great integrity for whom moral rectitude was as important as good physics, was accused of dishonesty. He would not be the last to irritate Bell by woolly thinking about quantum theory. And when Bell was a student there, he also worked with Peter Paul Ewald, the famous crystallographer, and in 1979, Bell wrote a letter to him, sort of thanking him, you know, for many, many years later. Your bad fortune in being cast away in Belfast was my good luck, which I think speaks to Bell's sort of character. So the numbers refer to a list of references that I'll put up at the end if you want to know that, or I'll share the slides with you later. But if I told you for everyone that you were interested in, we'd be here all day. So in 1949, after he graduated, Bell got a job doing accelerator physics at the UK's Atomic Energy Research Establishment at Harwell, and then sort of moved to another division in a different town, and then back eventually to Harwell. While working there, one of his coworkers was this woman, Mary Ross, that he ended up marrying later. She wrote much later about this period at Malvern. John was one of the group of young men, all with motorcycles, which they took to pieces regularly. And I like this quote for two reasons. One is just that I think it speaks to Bell's sort of not being this sort of head in the clouds theorist, but having a kind of really down-to-earth, realistic thing. You know, he's able to repair his own motorcycle. And it also made me think of the book Zen and the Art of Motorcycle Maintenance that I enjoyed reading, and there's some things about that maybe relate to Bell, but I'm not going to say anything more about that. So eventually, while he was working there, he became a consultant to the team that was designing the proton synchrotron at CERN. In 1953, the company offered this new policy of giving some of their employees paid leave to go and sort of further their educations, and so that's actually how he ended up going back to school and working with Rudolf Peierls to get his PhD. And so after he finished that, he took a job at CERN, where he stayed basically for the rest of his career.
Excuse me, do you know what his thesis was on?
Yeah, I'll talk about that in a second. So just another quote from Andrew Whitaker. Bell was always keen to help and on several occasions work with younger scientists. He had a delightful sense of humor and in personality was honorable and unassuming, though somewhat prone to irritation with those whose views on the quantum theory were not as pure as his own. He died suddenly of a stroke in October of 1990. Okay, so one slide about Bell's day job, that is to say sort of his regular work that he was getting paid for throughout his career, starting with his PhD thesis, which, as I mentioned, was with Rudolf Peierls, and basically there were two parts of it, and one of the two things that he did in his PhD thesis was to prove what's now known as the CPT theorem. It turned out this had been proved just earlier, by some other people, and so he's not usually credited with this, but I think it says something about his abilities as a theoretical physicist. So Peierls, after Bell's death, sort of wrote about this period. At the time, we had heard of experiments which seemed to reveal evidence for a negatively charged particle which was stable, but with mass less than that of the proton. The experimenters asked us whether this could be the antiproton. This seemed unlikely, but could it be firmly ruled out? Everybody expected particle and antiparticle to have the same mass, but was this strictly necessary? This was a problem after John Bell's heart. He did not like to take commonly held views for granted, but tended to ask, how do you know? In due course, he came up with the CPT theorem, that the results of any field theory must remain unchanged if one reverses the sign of the space coordinate end of time and interchanges particles and antiparticles. The theorem ensures in particular that any particle and antiparticle must have the same mass. Any evidence contradicting the theorem would be very hard to reconcile with our present basic physics. So far, no evidence has been found. Indeed, the experiment which had raised the question was not confirmed, obviously. So, during his career, he did this, he's a full-time researcher on sort of standard non-philosophical issues in particle and field and nuclear theory, and he wrote something like 80 papers on these sort of subjects that probably most of us have never read, at least most of them. His sort of most well-known contribution to so-called regular theoretical physics was in the late 60s, working with Roman Yakif on. He basically discovered the concept of an anomaly, right, of symmetry that's sort of broken by quantization, and Adler discovered this independently as well. So I think everybody who's taken quantum field theory knows about the Bell-Adler-Yakif anomaly. That was a very important contribution that obviously has influenced the development of quantum field theory. And also Bell played an important role in sort of being one of the people to really suggest the idea that the weak interaction should be described by a gauge theory. And there's a picture of him up here with Veltman, actually. And so, of course, Veltman and his then student, 't Hooft, eventually won the Nobel Prize for developing that idea. And throughout his career, he was also working on accelerator design, when he sort of in the spirit of rebuilding his own motorcycle or something. And some commentators on his work write that this part of his work, the sort of accelerator design stuff, must be kept in mind even by readers primarily interested in his contributions to the foundations of quantum mechanics and high-energy physics, because it shows the practicality and concreteness of his mind, which undoubtedly deeply influenced even his highly theoretical and philosophical thinking. So another quote, this is from Yakif and Shimoni. John Bell's attitude to his research on fundamental physical questions, rather than advancing new theoretical models, his publications are infused with a desire to know and explain existing structures, preferably in simple terms, in a simple model, phrases that occur frequently in his papers. If physicists come in two types, those who try to read the book of nature and those who try to write it, Bell belonged to the first category. He was conservative when it came to speculative and unconventional suggestions. He would prefer that unexpected contradictions not arise, that ideas flow along clearly delineated channels, but this would not prevent him from establishing what exactly is the case and accepting, albeit reluctantly, even puzzling results. This tension is seen in the anomaly paper, where after describing the phenomenon in the first part, a later section is devoted to an attempt at removing the anomaly, saving the chiral symmetry. But once he convinced himself where the truth lies, he would not allow his investigations to be affected by his inclinations, even if he remained disturbed by their outcomes. Such a commitment to truth, as he saw it, marked John Bell's activity in science and life. So now we turn to Bell's hobby, and this is actually how he described his work in the, what he called the philosophy of quantum mechanics as his hobby. And it really was sort of something that he did in his free time, as it were. So in the 1940s, he had heard of von Neumann's proof of no hidden variables and had sort of been bothered by that and kind of postponed the matter to later time. I think the sort of triggering event that really got him to start taking these issues seriously was in 1952 when, as he put it, he saw the impossible done. This, of course, refers to David Bohm's papers that came out then. His wife later wrote, "When the David Bohm papers appeared in 1952, I can remember how excited he was. In his own words, the papers were for me a revelation. When he had digested them, he gave a talk about them to the theory division at CERN. There were interruptions, of course, from Franz Mondel, with whom he had had many fierce arguments." During that decade between 1952 and the early 60s, obviously Bell was sort of coming to grips with the implications of the existence of Bohm's theory and how to reconcile it with von Neumann's theorem. And so finally in 1963, when he was on a sabbatical leave working at SLAC at Stanford in California, he sort of took the time finally to actually work on this issue. So there's this nice quote from him. So basically, since 1952, the hidden variables issue was never completely out of my mind. I always knew that it was waiting for me. So when I went to SLAC at the end of 1963, arriving in California the day after President Kennedy's assassination, it was a very odd experience to find everybody crushed. The quantum problems were very much in my mind, and that's where I wrote the papers that subsequently became notorious. First of all, I wrote a paper refuting all the proofs known to me of the impossibility theorems for hidden variables. While doing that, I saw that this problem of locality was vital. So that paper ended with this question: if you make locality a condition, can you then make a good proof of the impossibility of hidden variables? And the second paper answered that question. So those are, of course, the two famous papers that he wrote in 1964, one of which was accidentally unpublished for a couple of years. And then basically, we'll sort of say some more about some of these things later, but to finish the story in a nutshell, he's then spent 30 more years working on these issues, and I think everybody knows more about those because you've read some stuff from, you've read some of those papers. But I mean, he really made exceptionally important contributions in many areas of the foundations of quantum mechanics, and I mean, it's fair to say that not a single talk at this conference has happened that isn't in some major way sort of a continuation of a line of research that was really initiated by Bell. So I've tried to sort of list some of these here, but good. So an amusing quote from Despaignat, who was evidently also working at CERN in the 60s for a while. So he wrote, this is again sort of reflecting after Bell's death in the early 90s. In the 1960s, I had problems with quantum mechanics, and he had problems with quantum mechanics, but he did not know I had, and I did not know he had. I was once told by a friend that for some reason or other, he was sort of suspected of having some. And indeed, I had a confirmation of this when I spotted a heretical book on John's bookshelf, a most heretical book indeed, a book in French by Louis de Broglie. Can you imagine such a thing? That just made me laugh. And here's a nice picture of a conference on the foundations of quantum mechanics that Bell attended. I believe this was in the summer of 1990, so just a couple of months before he died. This was actually at Amherst College, which is literally across the river from where I teach currently. And you might recognize some people there, and maybe some of you were even there. I don't know. I haven't bothered to find out exactly who was there, but Merman was there, and Weisskopf was there, and some people I know from the Amherst area currently were there. Shelley, are you pointing at somebody that you recognize there? Okay. In any case, here's John Bell down on the right. And here's just another little amusing thing. In one of his interviews, Bell talks about a sort of chance occasion of meeting Bohr. He said, it was at the inauguration of CERN. I went up in a hotel lift with him. I didn't have the nerve to say, I think your Copenhagen interpretation is lousy. Besides, the lift ride wasn't very long. Now, if the lift had gotten stuck between floors, that would have made my day. Okay, so that sort of ends the biographical sketch portion of the talk, and I will move now to some remarks on Bell's continuing influence. So I found that Bell evidently continues to have an influence even in the popular culture. So here's some Dilbert cartoons about Bell's theorem that you can look at if you want. Do you want me to read them, or do you want to just... Okay, so it might be hard to see. Okay, so in the first frame here, Dilbert says, there, I think I've invented a way to send vast amounts of data without fiber optic cables. It's a simple application of J.S. Bell's theorem. He showed that if you break up a molecule and change the spin of one electron, the spin of the other electrons originally joined will immediately change too, no matter where they are. What do you think the fiber optic industry will give me for this? And the answer is, a horse's head in your bed. A reference to the Godfather movie, obviously. And in the second one, the garbage man is picking up the garbage from Dilbert and says, from the looks of your garbage, you've invented some sort of molecule bifurcation communicator. Yes, Einstein thought this type of thing might work. Physicist John Stuart Bell, with Stuart spelled wrong, incidentally, kind of fleshed it out in 1964, but you've really added something. Specifically, you've added this calculation error here. Good. We can all sympathize with that to some degree. So the first sort of topic on which I want to share some thoughts from Bell is the topic of locality. And I don't know, for most of these topics, I found some random quote of Bell's that sort of didn't fit into the rest of what I wanted to say. So here's that. This is a quote in which he's addressing this question that came up in our discussions a few days ago about these sort of two concepts of locality that are in play, what Bell called local causality on the one hand and what people call no signaling, some operationalist notion of locality. So Bell wrote, do we then have to fall back on no signaling faster than light as the expression of the fundamental causal structure of contemporary theoretical physics? That is hard for me to accept. For one thing, we have lost the idea that correlations can be explained, or at least this idea waits reformulation. More importantly, the no signaling notion rests on concepts which are should be desperately vague or vaguely applicable. The assertion that we cannot signal faster than light immediately provokes the question, who do we think we are? We who make measurements, we who can manipulate external fields, we who can signal at all, even if not faster than light? Do we include chemists or only physicists, plants or only animals, pocket calculators or only mainframe computers? So I think those are good questions. Good. So this shows the results of one of the questions of the poll I inflicted on you all the other day, but this is not your responses, this is the responses from that other conference at which this poll was taken. So I don't know if you can read this on the left. What is the message of the observed violation of Bell's inequalities? So far and away, the two most popular responses were local realism is untenable and unperformed measurements have no results. The least popular option was, let's not jump the gun, let's take the loopholes more seriously, and then a few people sort of gesturing in the direction of some notion of action at a distance or non-locality in the real world. I, of course, think this is wrong, as did Bell. So let's, and I put this other one up here just because there was some extra space, but this says, what is your favorite interpretation of quantum mechanics? 42% of people answered Copenhagen. Remember, this is not you, this is this other conference. So it's sort of because of this in a way that I felt embarrassed and wanted to have some more people answer these questions. 0% of the people answered de Broglie-Bohm theory in answer to this question. So suffice it to say that had Bell been at that conference, the answers would have been slightly different. Yeah.
I don't know if it's appropriate to interrupt with a question.
Absolutely. Remember, this is the beers and legs up on the chairs kind of
good,
talk. So.
Good. So there was, there is something I'm curious to know more about, if you know. The early quotes from Bell that you read a few slides ago about his coming to prove the theorem are quotes that certainly leave themselves open to the interpretation that he was proving something about what's required to get hidden variables. Later on, he turned around on that, and I'd be curious to know more of the history of
Good, so then you should pay attention to the next slide. Why is there this sort of lingering confusion about this issue of sort of whether he refuted local deterministic or hidden variable or realistic theories on the one hand, or just local theories? So here's some information basically that I was talking about with Howard yesterday about his 1964 paper. So contrary to something that people sometimes say, Bell really stressed the role of locality, and in particular sort of was thinking of the argument as what I think Shelley has sort of dubbed a two-part argument, in which the first part is like the EPR argument. I think it's clear when you go back to his 1964 paper and look for this, it's clear that that's how he was thinking about it from the very beginning. So literally the first sentence in the 1964 paper reads, the paradox of Einstein, Podolsky, and Rosen was advanced as an argument that quantum mechanics could not be a complete theory, but should be supplemented by additional variables. These additional variables were to restore to the theory causality and, of course, more importantly, locality. So I'm not... Let me at least finish this part, and then if you think there's a problem, we can talk about it. He then cites Einstein from the 1949 reply to critics paper, but on one supposition we should, in my opinion, absolutely hold fast. The real factual situation of the system S2 is independent of what is done with the system S1, which is spatially separated from the former. And then Bell sort of footnotes. So this quote is in a footnote, and he references that footnote 3 different times in the paper. So it's just, I think, completely clear that this is he was thinking of this as part of the argument. Unfortunately, when it comes to the conclusions of the paper, when he sort of summarizes what he's shown in the paper, he puts it this way. In a theory in which parameters are added to quantum mechanics to determine the results of individual measurements without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. Moreover, the signal involved must propagate instantaneously so that such a theory could not be Lorentz invariant. And so I should have put it in boldface, but of course the point of that is he says, in a theory in which parameters are added to the quantum mechanics, right? So that certainly, gives the impression that, at the end of the day, what he takes himself to have shown is sort of something about local realistic theories or local hidden variable theories. So the way, I think it's unclear, I would regard it as legitimately controversial how to sort of interpret exactly what he might have had in mind then, but my own interpretation of my reading of this is that he clearly had in mind the EPR argument from the beginning, and he was sort of naive to think that other people would just be able to understand the EPR argument and not sort of have in their head that Bohr had somehow refuted it, because clearly he didn't think that Bohr said anything that even remotely constituted a refutation of the EPR argument. So Howard wants to say something.
So I don't really disagree with much of what you're saying at all, except that in the first paragraph that you've highlighted two things, and the last one being locality, and you didn't highlight causality and.
Right.
And I think that in this paper, when Bell says locality, he means what he said in the last quote, which you read about, a mechanism whereby the setting of one measurement device can influence the reading of another, and that if he is, and I believe he's probably right, intuitively appealing to the EPR argument, that he is also using a notion of causality or determinism.
Okay, so I was going to ask you to clarify. Are you interpreting the word causality here to mean determinism? Is that?
Well, it's not clear exactly the sense in which he's using it there, but I think that he is using. If he's making an appeal based on the EPR argument, he's not merely using the notion of locality that he's using in this paper, that he is using something in addition to that, and that the causality and is actually an important part of that first quote. Yeah,
so I can see why you say that, and let's not talk about this too much right now. I mean, I think we probably won't settle it, but here's what I would say briefly in reply. To me, the other word that should have been highlighted in that first quote is the word argument, okay? So, I mean, to Bell, and, I agree with this, the EPR argument is an argument from locality to both causality/determinism and locality. So to whatever extent you think determinism plays a role too, fine, we get that from locality too. So it doesn't matter. It doesn't change this at all. But we'll come back to that very point later, so let's really not spend too much time on this. Good. And so then my sort of reading of the history is that Bell increasingly figured out over the years and decades that he was wrong to think that other people would so easily appreciate the EPR argument as he did. And I mean, you see him sort of like increasingly struggling with this in his papers over the years, sort of trying out different and ever better ways of like explaining that argument and calling ever more attention to its role. And what I see as sort of the culmination of this is toward the end of his career, he came up with a way of just sort of formulating explicitly what we mean by locality to sort of avoid, any possible verbal confusion or anything like that. And so this is something that has sort of been in the air a lot during this conference. I think on the first day, Tim was sort of trying to explain it in words, and maybe it's hard to capture that, so I thought I would just sort of show the picture and quote Bell describing this definition of locality. So this is like a space-time diagram of some events in regions 1, 2, and 3 as described, and he sort of describes what's going on here in the locality condition as follows. Full specification of what happens in 3 makes events in 2 irrelevant for predictions about 1 in a locally causal theory. So in a way, that's how he formulates local causality. He elaborates a little bit like this. A theory will be said to be locally causal if the probabilities attached to values of local beables in a spacetime region 1 are unaltered by specification of values of local beables in a space-like separated region 2, when what happens in the backward light cone of 1 is already sufficiently specified, for example, by a full specification of local beables in a spacetime region 3. And some important points that probably if we wanted to spend a whole hour talking about this, or if some crazy person wanted to say, like, write a really long paper about how to understand this definition of locality that you wanted to read, we could sort of do that. But just a couple of notes about this. Bell says that it's important that region 3 completely shield off from 1 the overlap of the backward light cones of 1 and 2. This is actually crucial to sort of the condition functioning properly as a definition of local causality. And he adds that it is also important that events in 3 be specified completely, otherwise the traces in region 2 of causes of events in 1 could well supplement whatever else was being used for calculating probabilities about 1. The hypothesis is that such information about 2 becomes redundant when 3 is specified completely. And so if you know, to whatever extent you accept this as a sort of valid, mathematical formulation of local causality, then the whole argument in a way becomes completely trivial, right? It's truly trivial now on the basis of this to sort of prove as little theorems that in a Bell EPR type setup you get factorization, and the EPR argument from locality to deterministic hidden variables can be made into a little theorem, and of course you can derive Bell type inequalities. And I don't want to sort of take the time to talk about how that goes because I think, you understand that, or sure.
I really wish that instead of saying locality all the time, you should use Bell's word and call it.
I thought I
local
just convinced
causality.
you yesterday that Bell himself made no distinction between these.
When he was being discursive, but when he wrote his papers, this is the term that he used.
Well, okay, so I mean, I think Howard and I have a disagreement about whether there are. So everybody agrees that there's some notion like this, which is somehow this very sort of realist formulation of, relativistic no action at a distance idea. And then on the other hand, there's this much more sort of operationalist attempt to capture something like that, which goes by the name no signaling. And then there's sort of this subsidiary disagreement about whether there's somehow two importantly different things that might get confused over here, namely something called locality on the one hand, and then something slightly subtly different called local causality on the other hand. And I don't think there's two different things there, and Howard does, but we can all talk about that later, anybody who's interested.
So could I make a comment about that?
I think that maybe we can leave the question for. It's very interesting. So there are people who have to believe, and so maybe we allow Javis to.
It's a 1 minute comment that's directly relevant.
I think we're okay on time, so I'm happy to.
Yeah, but no, but I guess that there are some people here who will have to take a pen soon.
Okay, this interchange
okay.
took much longer than my comment. Let me just say, just in support of what was said, that that it's misleading to call local causality simply locality, that one can identify, local causality is well defined, and I think it should be called classical locality, because it does not hold in Hilbert space.
Okay, so that's again something that could be discussed later, but your point is noted. Sean?
Well, yeah, but, well, the point is this. You see, Bell knew about Bohm's theory, and he knew that Bohm's theory was non-local in an appropriate sense. So, of course, if you define locality by no signaling, then Bohm's theory is local, and there was nothing to worry about. But you worried about the fact that the non-locality in Bohm's theory makes it on prima facie difficult to make relativistic. That was his worry, and fully relativistic. And of course, there he gives a definition of locality according to which Bohm's theory is not local. And then he shows that any theory must be non-local, so this non-locality, or call it whatever you want, call it habit if you like, but this habit-like property, which is shared by Bohm's theory and which is a necessary feature of any theory, is a quality of Bohm's theory because it's unavoidable rather than being a defect, that's all.
Yeah, so I mean, I agree with that, and I'm not sure if you intended this, but in a way, part of what you said, I think, answers your comment, but let's not discuss it. All I mean is that I think Jean is exactly right, that clearly Bell had in mind trying to formulate locality or local causality or whatever you want to call it in such a way that it would not just apply to classical theories, but would apply to sort of the preeminent example of a, prima facie non-local quantum theory, namely Bohmian mechanics, that he knew of. So I'm not really so sympathetic to the idea.
My definition of classical includes Bohmian mechanics. Classical
Okay, good.
ontology, not classical theory.
Okay, so speaking of ontology, the next subject on which I think there are some relevant remarks from Bell is the concept of beables, which a lot of people just use as if it was a perfectly ordinary, everyday kind of concept, and I suspect there may be some people in the room who literally have no idea what that word means. So I thought it might be worth letting Bell explain what he means by the word. So the first point is just that the concept of local beables plays a rather important role in Bell's formulation of local causality. And so to whatever extent you're sort of unwilling to talk about beables, then ipso facto you're unwilling to engage in a conversation about whether theories can be locally causal, at least as diagnosed by Bell's formulation. So Bell says this explicitly. It is in terms of local beables that we can hope to formulate some notion of local causality. And then some quotes just elaborating what he means by the notion of beables. The beables of the theory are those elements which might correspond to elements of reality, to things which exist. Their existence does not depend on observation. Indeed, observation and observers must be made out of beables, and this is like a phrase that he uses repeatedly in many, many papers, as I think Tim pointed out. He says elsewhere, you must identify in your theory local beables. The beables of the theory are those entities in it which are, at least tentatively, to be taken seriously as corresponding to something real. The concept of reality is now an embarrassing one for many physicists, but if you are unable to give some special status to things like electric and magnetic fields in classical electromagnetism, as compared to the vector and scalar potentials, then we cannot begin a serious discussion. And what he means here by beginning a serious discussion is trying to say in some kind of crisp and meaningful and sharp way, what do we mean when we say that a theory is local or not? I mean, that's what he's saying. We can't even begin to talk about that until we're willing to talk about stuff that exists, because the whole notion of locality, is stuff from outside the past light cone shouldn't be sort of causally influencing things that really happen here. And if you're just unwilling to have this discussion about sort of things that really happen or things that really exist, you can't begin a serious discussion. And also related to the concept of beables, it's, I think, crucial to keep in mind what, for Bell, the point of having local beables in the theory was. So let me read this passage. It would be foolish to expect that the next basic development in theoretical physics will yield an accurate and final theory, but it is interesting to speculate on the possibility that a future theory will not be intrinsically ambiguous and approximate, the way, of course, that he thought ordinary quantum mechanics was. Such a theory could not be fundamentally about measurement, for that would again imply incompleteness of the system and unanalyzed interventions from outside. Rather, it should again become possible to say of a system, not that such and such may be observed to be, but may be observed to be so, but that such and such be so. The theory would not be about observables, but about beables. And then sort of the key passage here. These beables need not, of course, resemble those of, say, classical electron theory, but at least they should, on the macroscopic level, yield an image of the everyday classical world. For, here he's quoting Bohr, it is decisive to recognize that, however far the phenomena transcend the scope of classical physical explanation, the account of all evidence must be expressed in classical terms. By classical terms here, Bohr is not, of course, invoking particular 19th century theories, but refers simply to the familiar language of everyday affairs, including laboratory procedures in which objective properties, beables, are assigned to objects. The idea that quantum mechanics is primarily about observables is only tenable when such beables are taken for granted. Observables are made out of beables. We raise the question as to whether the beables can be incorporated into the theory with more precision than has been customary. So this is sort of like his whole project in a way. And the highlighted passage I highlight largely because at this talk I had the experience, at this conference, I had the experience of finding many talks which sort of said things about beables or ontology, like, well, here's my theory, and here's now what the ontology is going to be. And in at least several cases, I had the experience that I simply didn't understand what the point of positing such an ontology would be. And that's even to whatever extent I understood what it could even mean. But it seems to me that there are some people who have lost sight of the idea that the point of positing an ontology is to yield an image of the everyday classical world. I think as Tim maybe put it on the first day, like, we want to sort of explain the data, and the data is, there's a table here and things like that, okay? Actually, though, as beautiful as this passage from Bell is, just yesterday another eminent theorist put the same point, I think, even more beautifully. So this was actually said yesterday, and I think it's exactly correct. I completely agree. Good. Now on to reality. So here's, I don't know, just a sort of amusing quote. So this is in the introduction that these two guys who interviewed Bell and then wrote up the interview in this magazine called Omni, sort of in their introduction, they write, "We first asked Bell over the telephone whether he himself felt that he had demonstrated that reality doesn't exist," which is, of course, what a lot of people, were saying at the time and still say. "He responded by warning us that he's an impatient, irascible sort who tolerates no nonsense." I mean, He did, however, agree to speak with us. In the flesh, we found him to be a soft-spoken man who talked extremely patiently to us for several hours. So I never met Bell, but the impression I get is that he's sort of has this dual character of being, on the one hand, like the gentlest and kindest and humblest person that many people ever knew, and on the other hand, he could just rip you to shreds, if you didn't, if he said something that you didn't agree with or that sort of challenged his views. So here's what I want to say about reality. So there's clearly a sense in which Bell was a realist. So here are some passages about this. He writes, "One wants to be able to take actually this is from an interview. One wants to be able to take a realistic view of the world, to talk about the world as if it is really there, even when it is not being observed. I certainly believe in a world that was here before me and that will be here after me, and I believe that you are part of it." I guess he's talking to the interviewer there. "And I believe that most physicists take this point of view when they are not being pushed into a corner by philosophers. In the beginning," this is a really interesting quote, "In the beginning, natural philosophers tried to understand the world around them. Trying to do that, they hit upon the great idea of contriving artificially simple situations in which the number of factors involved is reduced to a minimum. Divide and conquer. Experimental science was born. But experiment is a tool. The aim remains to understand the world. To restrict quantum mechanics to be exclusively about piddling laboratory operations is to betray the great enterprise. A serious formulation will not exclude the big world outside the laboratory." And elsewhere he writes, actually this might also be from an interview, "The pragmatic approach has undoubtedly played an indispensable role in the evolution of contemporary physical theory. However, the notion of the real truth, as distinct from the truth that is presently good enough for us, has also played a positive role in the history of science. Thus, Copernicus found a more intelligible pattern by placing the sun rather than the earth at the center of the solar system. I can well imagine a future phase in which this happens again, in which the world becomes more intelligible to human beings, even to theoretical physicists, when they do not imagine themselves to be at the center of it." So Bell was a realist, right? It's clear. Yeah? Good. So Bell was also an anti-realist. So let me explain. I packed a lot on here, so I don't know if you can even read this, and I can barely even see it on my own screen here. From the preface, actually, to his book, the first edition of which came out in 1987, he writes, "Despite the impossibility proofs, the Pilotwave picture of de Broglie and Bohm exists. Moreover, in my opinion, all students should be introduced to it, for it encourages flexibility and precision of thought. In particular, it illustrates very explicitly Bohr's insight that the result of a measurement does not in general reveal some pre-existing property of the system, but is a product of both system and apparatus. It seems to me that full appreciation of this would have aborted most of the impossibility proofs and most of quantum logic." And just some other quotes where he makes essentially the same point, but I think it's really important to appreciate. So in one of his early papers, one feature of the Pilotwave theory's account of basically what's going on with the spin 1/2 particle is this. We have here a picture in which, although the wave has two components, the particle has only position. The particle does not spin, although the experimental phenomena associated with spin are reproduced. Thus, the picture resulting from a hidden variable account of quantum mechanics need not very much resemble the traditional classical picture that the researcher may secretly have been keeping in mind. The electron need not turn out to be a small spinning yellow sphere." I love the fact that he calls it yellow. Like, why? It's probably some chemistry book that he used in college that had them being yellow or something. Yeah. Good. So, good. So then Bell and Pauli agree about that. So continuing the quote, a second way in which the scheme is instructive, that is Bohm's theory, is in the explicit picture of the very essential role of the apparatus. The result of a spin measurement, for example, depends in a very complicated way on the initial position of the particle and on the strength and geometry of the magnetic field. Thus, the result of the measurement does not actually tell us about some property previously possessed by the system, but about something which has come into being in the combination of system and apparatus. Of course, the vital role of the complete physical setup Of course, the vital role of the complete physical setup we learned long ago, especially from Bohr. When it is forgotten, it is more easy to expect that the results of the observations should be preserved even by the hypothetical dispersion-free states of which quantum mechanical states may be composed. That is sort of a hidden variable theory idea. The model illustrates how the algebraic relations valid for the statistical ensembles, which are the quantum mechanical states, may be built up in a rather complicated way. Thus, the contemplation of this simple model could have a liberalizing effect on mathematical investigators. Similarly, in physics, the only observations we must consider are position observations, if only the positions of instrument pointers. It is a great merit of the de Broglie-Bohm theory to force us to consider this fact. If you make axioms rather than definitions and theorems about the measurement of anything else, then you commit redundancy and risk inconsistency. And again, similarly, when it is said that something is measured, it is difficult not to think of the result as referring to some pre-existing property of the object in question. This is to disregard Bohr's insistence that in quantum phenomena, the apparatus as well as the system is essentially involved. If it were not so, how could we understand, for example, that quote measurement of a component of angular momentum in an arbitrarily chosen direction yields one of a discrete set of values? When one forgets the role of the apparatus, as the word measurement makes all too likely, one despairs of ordinary logic, hence quantum logic. When one remembers the role of the apparatus, ordinary logic is just fine. Good, so Bell is a realist and in another sense, an anti-realist. This is crucial to keep in mind always. So I wanted to make the point that there's a kind of trading on this ambiguity of the sense of the word realism when people talk about experiments having refuted local realism. So it took me about 2 seconds to go onto Google and type local realism and find some nice recent paper. So the first paragraph of the abstract of this paper that just came out a couple weeks ago, the violation of a Bell inequality is an experimental observation that forces the abandonment of a local realistic viewpoint, namely one in which physical properties are probabilistically defined before and independently of measurement, and in which no physical influence can propagate faster than the speed of light. Okay? So this is how the ordinary physicist on the street who hasn't read Bell, and unfortunately it's how many people, even still in the foundations community, understand Bell's theorem, that it refutes local realism. That is to say, you have to either give up this notion that there's these sort of pre-existing properties which are revealed by measurements, or you have to give up relativistic locality. And of course, if that's really the choice, then it's obvious which one you should give up. But this is simply wrong. Or at best, it's a kind of equivocation on the word realism, saying, Bell was a realist and he assumed locality, and there's maybe some sense in which the notion of realism, in the sense in which Bell was indeed a realist, okay, fine, maybe something like that is sort of a premise that you need before you buy into the game of even accepting Bell's definition of locality. Okay, but once you do that, that's it. Okay? There's no additional assumption of realism of the other sort, realism of the hidden variables sort, realism of the sort about which Bell was an anti-realist. Okay? There's simply no such assumption. And so this is exactly this misconception from his original paper that Bell was sort of struggling against throughout his career. I think one of the best passages about this is from the famous Bertelsmann-Sachs paper. He writes, "It is important to note that to the limited degree to which determinism plays a role in the EPR argument, it is not assumed but inferred. What is held sacred is the principle of local causality or no action at a distance." And I interject here that, he says determinism, but he could just as easily have said hidden variables or, quote, realism in this sort of sense of meaning basically hidden variables, or, there are sort of a bunch of other things. Tim recently introduced this phrase that I like very much, the fallacy of the superfluous adjective. So if anybody knows what I'm talking about, then I find that a helpful way to think about this. Continuing the quote, it is remarkably difficult to get this point across, that determinism, or realism, or hidden variables, or whatever you want to call it, is not a presupposition of the analysis. There is a widespread and erroneous conviction that for Einstein, determinism was always the sacred principle. The quotability of his famous "God does not play dice" has not helped in this respect. And there's a footnote from Einstein that I've reproduced here. There's a widespread and erroneous conviction that for Einstein, determinism was always the sacred principle. And then Bell writes, and his followers, right, by which he obviously means himself. And he there says explicitly, my own first paper on this subject, the one that I was quoting from earlier from 1964, starts with a summary of the EPR argument from locality to deterministic hidden variables. But the commentators have almost universally reported that it begins with deterministic hidden variables. And tragically, that seems to remain true, or at least the experimental physicists are still under this confusion. Good. Okay, good. Now some slightly shorter and perhaps slightly less important things, but a few more topics like this. When I wrote this last night, the word "what" was written with a 3-letter acronym, the first and last letters of which were W and F. But I decided it would be more appropriate to just change it to "what." So this is something that a lot of people still think about. There's this nice quote from Bell, again from an interview. When I came to learn quantum mechanics, which I did very soon after I went to the university, I was dissatisfied with the expositions I found. This wave function, one never knew whether it was something real or some kind of bookkeeping operation. And I think it's fair to say that this is something that we are continuing to struggle with. On the plane ride over, I was reading papers out of this nice book that came out recently. So the quotes here from Bell just indicate that those of us who are still slightly confused about how to understand the wave function are in good company, in the sense that Bell himself seemed to sort of think about it in slightly different ways at different times and in different contexts. So clearly one way that he thought about it was as what we would call now a non-local beable. He says this explicitly. The state vector also, in addition to some other stuff in some whatever theory he was talking about here, also we consider as a beable, although not a local one. And there are some nice passages where he sort of says how he envisions that, what he takes that to mean. So, for example, in the context of Bohm's theory, he says, note that in this compound dynamical system, right, the particle and the wave is supposed to be just as real and objective as, say, the fields of classical Maxwell theory, although its action on the particles is rather original. No one can understand this theory until he is willing to think of psi as a real objective field rather than just a probability amplitude, even though it propagates not in 3 space, but in 3n space. And similarly, I believe this is from the letter that he sent to you that you quoted from Giancarlo earlier. As regards the wave function and the density of stuff, I think it is important that this density is in the 3n dimensional configuration space. So I have not thought of relating it to ordinary matter or charge density in 3 space. Even for one particle, I think one would have problems with the latter. So I'm inclined to the view that you mentioned after it is, something from a letter that you had written to him. And it has to be stressed that the stuff is in 3n space or whatever corresponds in field theory. Now, unfortunately, I don't know of Bell having contemplated the possibility that the wave function should be regarded as a law. Perhaps he did, but he does, in this interesting passage, I think, suggest a rather different view in which the wave function might be understood as somehow a kind of indirect representation of or characterization of some local beables that might be in the theory. And he says this in the context of sort of ordinary quantum mechanics, but I think it's still somewhat interesting. Could it be that the violation of local causality is due to an incomplete specification of the beables, not so long as we stick to the list of beables recognized in ordinary quantum mechanics, the settings of switches and knobs and currents needed to prepare the initial unstable nucleus? For these are completely summarized insofar as such predictions are possible in quantum mechanics by the wave function. So, right, that's a rather different view about how you might understand the wave function, that it's somehow a kind of indirect summary of the disposition of a bunch of local beables. Good. So we turn now to philosophy, and this is really the sort of... What's that? The conditional wave function. I like that, but I don't know what you mean. I see. Good. So here's a nice quote from Bell where he's sort of reflecting on his thoughts about the subject of philosophy. I was a bookish sort of child, much in the local public libraries. I was hostile to the idea of sports. I regret it now. I've grown up to be a 7-stone weakling. I was, brought up in the Church of Ireland. I was even confirmed by a bishop. But in my adolescent years, I began to wonder if it was really true what they told you. Does God exist? Questions like that. So like many children, I started looking for answers. One place to look, I thought, was philosophy. I was reading thick books on Greek philosophy, but very soon I became disillusioned with philosophy. I found that the business of the good philosophers seemed mainly to refute the bad philosophers. There didn't seem to be much else. The next best thing seemed to be physics. Although physics does not address itself to the biggest questions, still it does try to find out what the world is like, and it progresses. One generation builds on the work of another instead of simply overturning it. So I have no comment on that. I just find it amusing. And here's a couple of things that other people, commentators on Bell have written about sort of philosophy. So Andrew Whitaker wrote in Jeremy Bernstein's article, Bell talks about a rather brief interest in philosophy, mainly Greek philosophy during his teenage years. And this person, Leslie Kerr, a friend of Bell's from college, and then also a co-worker with him later at Harwell and Malvern, found him interested in and well able to argue on important philosophical matters. This was the heyday of logical positivism, at least in Britain, with the predominance of A.J. Ayer. Bell was, at first, a great upholder of this philosophy, which he felt had made all the great problems of philosophy irrelevant. But he then changed his mind as he became convinced that logical positivism must lead to solipsism. For Kerr, Bell's explanation was the first refutation of logical positivism he had heard, and he says that, like most of Bell's idea, it was beautifully simple and convincing. And Despaignat wrote, I am convinced that the notion of a mind-independent reality does make sense, but I take at the start a quite agnostic standpoint as to whether it is scientifically describable or not. And in view of the turn physics has actually taken, I am inclined to consider that what science describes is merely an empirical reality, that is, nothing else than the set of phenomena in a Kantian sense of the word. In other terms, a set of collective appearances. To John Bell, this idea was absolutely repellent. Indeed, I remember that beginning in 1990, I sent John a preprint of mine, the title of which contained the expression empirical reality. And he sent me back something, either my own preprint or a paper by him, I don't remember, on which he had diagonally written in large letters, I do not believe in empirical reality. Again, amusing. Good, and so some interesting comments by Bell on another issue that relates closely to the point I was making earlier about the point of local beables being to sort of reproduce the macroscopic world that we have some kind of direct perceptual access to. So Bell makes some remarks that are relevant to that. Solipsism cannot be refuted, but if such a theory is taken seriously, it would hardly be possible to take anything else seriously. So much for the social implications. It is always interesting to find that solipsists and positivists, when they have children, have life insurance. So he's obviously saying that you sort of can't practice this consistently because it's absurd. He writes somewhere that theoretical physicists live in a classical world looking out into a quantum mechanical world. And then this other quote I like very much. To what extent are the various sort of candidate quantum theories fictions? They are like literary fictions in that they are free inventions of the human mind. In theoretical physics, sometimes the inventor knows from the beginning that the work is fiction. For example, when it deals with a simplified world in which space has only 1 or 2 dimensions instead of 3. More often, it is not known until later when the hypothesis has proved wrong that fiction is involved. When being serious, when not exploring deliberately simplified models, the theoretical physicist differs from the novelist in thinking that maybe the story might be true. Perhaps there is some analogy with the historical novelist. If the action is put in the year 1327, the Pope must be located in Avignon, not Rome. The serious theories of theoretical physics must not contradict experimental facts. When we invent worlds in physics, we would have them to be mathematically consistent continuations of the visible world into the invisible, even when it is beyond human capability to decide which, if any, of those worlds is the true one. Literary fiction, historical or otherwise, can be professionally good or bad, I think. We could also consider how our possible worlds in physics measure up to professional standards. In my opinion, the Pilotwave picture undoubtedly shows the best craftsmanship among the pictures we have considered. But is that a virtue in our time? pressing question still today. So one more of these topics, which is relativity. There's this nice passage from one of the interviews with Bell that is in this book called The Ghost in the Atom, that talks about relativity and philosophy in a kind of way that's interesting, so I just share it without comment. So the interviewer asks sort of basically what are the implications of the experiments showing violations of Bell's inequality, and Bell responds, "For me it's a dilemma. I think it's a deep dilemma, and the resolution of it will not be trivial. It will require a substantial change in the way we look at things. But I would say that the cheapest resolution is something like going back to relativity as it was before Einstein, when people like Lorentz and Poincaré thought that there was an ether, a preferred frame of reference, but that our measuring instruments were distorted by motion in such a way that we could not detect motion through the ether. Now, in that way, you can imagine that there is a preferred frame of reference, and in this preferred frame, things do go faster than light. But then in other frames of reference, when they seem to go not only faster than light, but backwards in time, that's an optical illusion." And the interviewer, undoubtedly sort of taken aback by this radical, blatantly unscientific and crazy idea, says, "Well, that seems like a very revolutionary approach." And Bell responds, "Revolutionary or reactionary, make your choice. But that is certainly the cheapest solution. Behind the apparent Lorentz invariance of the phenomena, there is a deeper level which is not Lorentz invariant." And this continues. The interviewer says, "Of course, the theory of relativity has a tremendous amount of experimental support, and it's hard to imagine that we can actually go back to a pre-Einstein position without contradicting some of this experimental support. Do you think it's actually possible?" And so Bell explains, "Well, what is not sufficiently emphasized in textbooks, in my opinion, is that the pre-Einstein position of Lorentz and Poincaré, Larmor, and Fitzgerald was perfectly coherent and is not inconsistent with relativity theory. The idea that there is an ether and these Fitzgerald contractions and Larmor dilations occur, and that as a result the instruments do not detect motion through the ether, that is a perfectly coherent point of view." And the interviewer says, "And it was abandoned on grounds of elegance?" And Bell says, "Well, on grounds of philosophy." So that's what I find so interesting. "That what is unobservable does not exist, and also on grounds of simplicity, because Einstein found that the theory was both more elegant and simpler when we left out the idea of the ether." Skipping a little bit. "The reason I want to go back to the idea of an ether here is because in these EPR experiments, there's the suggestion that behind the scenes something is going faster than light. Now the mystery is, as with Lorentz and Poincaré, that this ether does not show up at the observational level. It is as if there is some kind of conspiracy, that something is going on behind the scenes, which is not allowed to appear on the scenes. And I agree that that's extremely uncomfortable." So the point here is that sort of Bell, I think, was quite open to something that most of us would consider crazy, and I think he sort of understood what happened 100 years ago in the community becoming convinced that this idea of a privileged reference frame or an ether was wrong. I think he understands that a lot better than sort of the physicists who learn about this from the textbooks. But there's a big however, okay, because Bell was definitely not of the view that sort of that's what you have to do and that's the only way to make sense of things. So here's sort of another of Bell's perspectives on how to reconcile his results with relativity. For myself, I see the GRW model as a very nice illustration of how quantum mechanics, to become rational, requires only a change which is very small on some measures. And I am particularly struck by the fact that the model, so this is basically his flash ontology understanding of GRW, that the model is as Lorentz invariant as it could be in the non-relativistic version. It takes away the ground of my fear that any exact formulation of quantum mechanics must conflict with fundamental Lorentz invariance. Good, so I'm basically done. I don't really know what the conclusion should be, so here's something that Bell wrote actually about Dirac, at least part of which seems sort of very appropriate as a description of Bell himself, so I'll share this with you. "I know that many people here are practical physicists that know very well that you can get along without paying any attention to these foundational difficulties, and many of these people are so confident in their practice that they can even dismiss the existence of the foundational difficulties. I am always wanting to argue with such people, but I have learned by experience that there is no hope whatever of converting them." Perhaps some resonance with some of us from this week. And I think that those people would only really admit the existence of these problems when they are solved, and then when they see a nice, definitive, relativistically invariant solution, then they would look back and say, yes, there was a problem. And Dirac was very conscious of how different things could look according to whether you were looking forward or backward from one side or another. And he had a tremendous ability to dissociate himself from the common perception, from the obvious idea, and that should be an object lesson to all of us. And so I think especially this part that I highlighted is a good description of what made Bell really sort of unique. It's as if he was sort of standing on this mountaintop looking down at all of these issues that sort of other people couldn't sort of see the alternatives to. And so in a very admittedly bizarre way of concluding a talk like this, I will put up one more quote, which is not from Bell, but from some other recent commentators, and invite you all to share in diagnosing the errors in this quote. So this is something that Bertelsmann and Seilinger wrote in the preface to their conference proceedings from this conference that basically happened as a celebration of Bell's life. So they wrote sort of the following, kind of summarizing Bell's contributions to the foundations of quantum mechanics. While John Bell had flung open the door widely for hidden variable theories by showing the flaws in von Neumann's and other proofs, he immediately dealt them a major blow. In 1964, he showed that any hidden variable theory which obeys Einstein's requirement of locality, i.e. no influence traveling faster than the speed of light, would automatically be in conflict with quantum mechanics. While a very tiny experimental loophole in principle remains for local realism, it is a very safe position to assume that quantum mechanics has definitely been shown to be the right theory. Thus, a very deep philosophical question, namely whether or not events observed in the quantum world can be described by an underlying deterministic theory, has been answered by experiment, thanks to the momentous achievement of John Bell. It is most interesting to note that despite his own theorem, John Bell continued to be an advocate of realistic hidden variable theories, which now, according to his own findings, have to be non-local. Therefore, he became an advocate of theories proposed by Girardi, Ramini, and Weber, Peierls, and Gisin, theories that, no matter how little, deviate from quantum mechanics and thus might be ruled out by experiment someday. Thus, even if John Bell in the end might not have turned out to be on the right side when it comes to the fundamentals of the interpretation of quantum mechanics, this should never be held against him. In contrast, he was one of the few, like Albert Einstein, who realized how extremely strange the consequences of quantum mechanics, if it should finally turn out to be the ultimate correct theory, are for our view of the world. And it is a sign of his high moral distinction that he was not at all willing to give in easily. So I'll just say that that disgusts me, and I hope that my talk and the rest of this conference helps you appreciate why that's so disgusting. And if people want to sort of say specifically what they think is wrong with this, I'd be happy to hear that, but that's all I'm going to say, so thank you. Yes, so there exists here a list of references, but I don't know if I should leave that up or go back to the quote that I ended with. Anybody who wants this list, I can email it to you or something. So.
You pointed out that he was working in the accelerator.
Yeah.
And so it was also very practical. I would like to stress, probably many people have heard this by me, that he was considering that one of his duties. Because I remember just when he was in Trieste walking in the Miramare Park, and he told me, look, Giancarlo, you know how I am fond of foundational problems and I would take them seriously. However, I think that it's a luxury to do this, and this is why I get my salary working in evaluating the orbit of the accelerator. Then I answered to him, John, you are putting me in a very bad situation because it's 30 years that I am working on foundation. And he said, oh no, Giancarlo, you have forgotten a fundamental thing. In this 30 years, you have grown up hundreds of students in quantum mechanics. This justifies your salary, which is typical of John.
Yeah.
So this is just a tiny comment because in that last bit about relativity with Bell, he says something which I assume he wasn't confused about, but maybe it's worthwhile pointing out.
Should I put it up?
Which is just that about throwing in using a foliation and this thing about elegance and so on.
Yeah.
Which is just, the suggestion you get there. You could say the ether theory was going backwards in terms of space-time structure from what we call neo-Newtonian or Galilean space-time, which doesn't have any absolute notion of velocity, back even to Newton's theory of absolute space and time, where things have absolute velocities. Right. And the suggestion that you add a foliation to a relativistic space-time is just an entirely different space-time structure. It's not going backwards. And so one shouldn't think that way, that it's going back to any classical picture of space-time. It's a relativistic space-time with a little bit of extra structure.
I see.
The thing about conspiracy, and again, I guess my view is, if you throw a foliation in and write down something simple and non-contrived and obvious, and then analyze it and find that the foliation turns out not to be empirically accessible, doesn't sound conspiratorial to me. I mean, I find conspiracy in fine-tuning of constants of nature or something like that. I mean, I have a feel for what conspiracy is. That just doesn't seem to me conspiratorial. Yep. I'm not sure, I'm not sure. I would be interested to know what Bell, how Bell would have made sense of this idea, because it does seem to me that the idea that, well, everything physically real must be accessible to us at macroscopic scale or something, unless you think God set things up and said, I'm going to be nice to you guys, which I don't believe. I'm not quite sure where the discomfort comes from. There's just a small comment.
I completely agree.
Yeah, about the last quote, which I found surprising, is maybe the Boltzmann's part. Because Zeilinger is sort of so committed to so-called quantum information, whatever that is, so that I'm not so surprised that he doesn't understand Bell. But Boltzmann was a friend of Bell, if I understand, and so they spoke, and it's sort of, it's a little bit like Pies. Pies was working from the Institute with Einstein. Obviously, he never understood Einstein. When Einstein asked him if the moon was there when nobody looked, he clearly did not, he reports that, but he clearly missed the point of what Einstein wanted to say, and it seems to be the same thing happened with Boltzmann and Bell. Yeah. Sort of
Clearly.
pity.
I think there is another kind of psychological mechanism that has contributed to the misconception that Bell was assuming hidden variables from the start, and that his result concerns only hidden variables theories, and that is that in later versions of the argument, particularly the one involving the Clauser-Holt-Shimoni-Horn inequality, where everything is expressed in terms of probabilities of outcomes, conditional probabilities of outcomes given some lambda. It's kind of very suggestive to think, what is the lambda? Of course, that is hidden variables. Right. So all this calculation about conditional probabilities, conditioning on lambda, must be about hidden variables theories.
I agree. And people, many textbooks and sort of commentators on Bell's theorem say explicitly that, and by the way, this includes the authors of the CHHS paper that you mentioned. I mean, they explicitly say the lambda that sort of shows up in the mathematical derivation describes hidden variables, which it needn't. I mean, if hidden variables means something either supplementary to or distinct from the quantum state, then there's no reason at all that that mathematical symbol needs to have sort of that restrictive meaning. It can perfectly well just mean the quantum state and nothing else, and the derivation still works just fine. But I agree.
In the 10th anniversary of John Bell's death, and I claim, and I feel that this is a nice place to claim, that 90% of the talk that I have heard at that conference would have been rejected completely by John Bell.
Yeah.
There is a paper about that called the John Bell scandal, no? There is a paper, somebody complaining about that conference, and I forgot whom, but the paper is called the the John Bell scandal about this conference? I mean, somebody.
I've never heard of that. I'd be interested to know about that if you can give me a reference. Yeah.
At the risk of infuriating you, would it be possible for you to briefly sketch what you find particularly disgusting?
About the quote?
Yeah.
Yeah, I mean, I'll summarize. There's, I could probably go on for many minutes about
I think
that.
you shouldn't answer the question.
You don't think I should answer the question?
No, you shouldn't.
No, I'll answer it in a very factual and straightforward way. I think it's clear that the authors simply fail to appreciate what Bell's argument was, and so they have misunderstood him in a profound way. And what I actually kind of find disgusting, though, is sort of the end part where they basically say, Bell was such a wonderful man that we shouldn't hold against him the fact that he was completely wrong in his ideas about sort of which theories were reasonable to pursue and that kind of thing. Because to me, and maybe this is sort of what I probably should have just actually said as the conclusion of my talk, for me, yeah, like all these sort of personality characteristics of Bell, I have the impression that he really was a wonderful man, but to me, the more important and fundamental thing is that he was profoundly right about virtually everything he said. And so to say this, right, to say that we should love him even though basically he was kind of wrong about everything is just really, really off target.
Can I mean, just to help Jörg as well, I find this I haven't read this whole thing, so maybe I'm not being fair, but from what I see up here, it also looks profoundly dishonest in the following sense. The top part says, well, anything would automatically become in conflict with quantum mechanics, and quantum mechanics turned out to be right. And then in the latter part, he only talks about Bell's interest in collapse theories that deviate from quantum mechanics. So you could put those two together and say, oh, Bell tried to get out of his own result by saying quantum mechanics must be wrong. And they don't dare mention Bohmian mechanics, which was the other thing he advocated all the time. And that doesn't deviate from the experimental predictions of quantum mechanics. So somebody who didn't know the situation, reading those two paragraphs anyway, would have a completely incorrect understanding of Bell's interest in the theories like GRW and Bohm and why he was interested in them. They would draw clearly a conclusion from those two things that's just the opposite of the truth.
Yes, but you see, there is a big difference between refuting somebody's views and misrepresenting them. And there is also something, as you say, disgusting when you agree with somebody for saying the opposite of what he says, like Gell-Mann commenting on Boltzmann socks, which I mentioned in my lecture. But of course, the funny thing here is that GRW, of course, is also non-local. So if Bell turned to alternative to quantum mechanics because he wanted to escape from non-locality, then they missed the point to an enormous extent, because of course Bell shows that GRW type theory must also be non-local in some appropriate sense, and they are. So, the misrepresentation of his is very, and what is disgusting, to use your word, is simply that you are sort of praising somebody while totally misrepresenting his views. I mean, again, they could disagree with him, or like Gell-Mann could disagree with him, but they couldn't agree with him and then say the opposite, and here they sort of disagree but misrepresent his views.
Yep.
I don't feel so much disgusted by what is written, at least the first section there, by Zeilinger, I think. Because he writes very clearly that we are talking about non-local hidden variables. So this is already better than what Gell-Mann wrote. So clearly he says that violation of Bell's inequalities means the end of local hidden variable theories. And I think that in the mind of Zeilinger, deterministic non-local theory is unacceptable to begin with. He didn't write it, okay, that's not very explicit. But for many physicists, deterministic non-local theory is unacceptable because it is conspiratorial.
I don't understand that at all.
The world is unacceptable then, that's the problem. Bell shows that the world is unacceptable. Bell shows that it's not a question of hidden variable. The hidden variable are shown to be the way to save locality in the EPR argument.
So
otherwise, non-locality is already accepted from the start.
Let me try to understand your comment. You're saying for many
For
people,
me-
deterministic non-local theories are unacceptable. Are they unacceptable because they're deterministic, or
No,
are they unacceptable because they're non-local?
they conspire to respect the no signaling condition. And this is difficult to understand.
But the point is that you should also distinguish between determinism at the fundamental level of the theory, or determinism in the sense that the pre-existing values that explain the perfect correlation. I mean, the so-called spin values, which are explaining the perfect correlation, this is, of course, something which sometimes people call determinism, but has to be distinguished between whether the underlying theory is fully deterministic or not.
So
In GRW, there'll be the spin value even though the theory is stochastic.
So I'm not sure, but it sounds to me like you are conflating two different ideas, one of which is sort of regular determinism, and one of which is the idea that Bell called superdeterminism, which is indeed this idea that somehow the initial conditions are conspiratorially chosen to trick us.
No, it's rather he's talking about, in Bohm theory, it would be the quantum equilibrium that prevents you from using this perfect correlation, this sort of action at a distance in order to send signals, you see.
But what's conspiratorial about that? There's nothing
It's
whatsoever
very natural,
conspiratorial about that.
Equilibrium is more natural than none.
Anyway, let's talk about that later, because some other people have comments and questions.
A little earlier in your talk, you showed an abstract from a recent publication,
Yeah.
I guess a couple weeks ago, and then you said something about what they had written in the abstract. You didn't like that or found unsatisfactory.
Yeah.
Could you similarly comment on that, what specifically in that abstract was objectionable?
So it's basically that they sort of clearly and explicitly endorse this idea that what's being tested by the experiments is the conjunction of two distinct ideas, one of which is locality, and the other of which is something like hidden variables or sort of realism, in the sense in which Bell was certainly not a realist, right? This idea that when you make a measurement, you're sort of discovering the value, or sort of revealing the value of some pre-existing thing, right? And that's literally what people mean whenever they use the phrase local realism. They mean, well, there's sort of these two ideas, locality and quote-unquote realism, which basically means like deterministic hidden variables theories or something. And they have this idea that it's these two things jointly which imply the Bell inequality that then the experiment tells us is wrong. And so then we sort of get to have a philosophical discussion or something about which one of those we want to give up. And the point is just that that's wrong. That's just a wrong understanding of what the premises of Bell's theorem are.
I know from personal experience that it is very easy to misunderstand things. I would like to warn against the idea that people have bad characters or unpleasant personalities, or that they are dishonest when they misunderstand something. Because I think this is frightening for the younger generation. Young people have the right to occasionally misunderstand something and not be punished by being declared to be dishonest or whatever. So let's just admit that we occasionally misunderstand something and that we may make a mistake.
So I don't really disagree with that as a matter of sort of moral principle as expressed, but I think I would be more sympathetic to that comment being applicable if it hadn't been the case that Bell literally spent 30 years, admittedly only of his free time, trying to clarify precisely this issue. And, for example, the kinds of people who wrote the passage that I put up at the end that I said that I found somewhat nauseating, certainly those people, editors of a volume from a conference like celebrating the contributions of John Bell to the foundations of quantum mechanics, surely those people, if anybody, were in a position to have tried to understand what Bell actually said and to represent it correctly and honestly.